What?
Tomorrow is October.
It is?
It's on the 33rd.
Okay. Now, okay, here's the thing I want to talk about today. Let's start with kind of an easier base problem. I want to go with something like, let's go with 2x squared plus 4x plus, let's go with 2. Okay. We're going to stick with something like this. We'll kind of walk through the parts together, talk about how it works. So what this is supposed to be representing, it's supposed to be representing a function, a polynomial that we're used to drawing and graphing. And the idea, what the goal is on this type of problem is to figure out that maximum or minimum point on the graph. Does it have a max or min? And if it does, what one is it and where is it found? So it's that point between like increasing or decreasing to increasing. So like what I mean by that, it's like we're looking at the point where it's continuous and we're looking at a hilltop or a valley type of thing. So that's going from increasing to decreasing. It's like they call it a critical point. And that's what we're looking at today. The thing is we have to put everything together, like everything we've learned up to this point. So like on this type of graph, it is definitely the tails are going up, so the end behavior tails are up, and they're going the same direction. So the tails go up somehow like that.
So it's a parallel.
Okay, so we already know that, right? It's a power of 2, so it's a parabola. So we're kind of putting some pieces together, what it's going to look like. So in this case, knowing that the tails go up, this graph has a minimum. Agreed?
Yep.
Like just knowing that simple fact, it's a parabola, and the tails go up, so it has to have a minimum point. I want to know where the minimum's found, the exact lowest point on the graph. That's what I want to look for. Okay, we've done these before. It could be as easy as figuring out where that actual vertex is using completing the square. But the goal today is we're going to try to go one more step today, where we're going to look at cubic functions where we can't just figure out one spot. It might be 2 spots, and we're going to look at those. And we're going to try to see if it's possible to do a problem like that. Okay, these numbers may not work out nice and pretty. I'm just going to kind of put them together and see what we have. Okay, question.
We have to do that stupid dot that the parabola goes around.
You mean like the directrix, like the plane and like the focus on the inside?
Yeah.
No, we're not doing that.
Not at all.
Not at all.
This one very.
Nope. Okay. All right. Well, let's go through the basics when I want to talk about the minimum part on that graph. Okay. So here's the idea. I want to keep drawing, so maybe we can kind of figure out where it's going to be. So it's the tails go up. I'm going to factor out. So I'm going to try to find x-intercepts and y-intercepts. I know my y-intercept is a positive 2. I can see that right away. Because if I plug in a bunch of zeros, my y-intercept is 2. Okay, so that's nice and easy to see. But for the x-intercepts, I do have to factor this thing apart. So for x-intercepts, if I factor out a 2, I'm left with x squared plus 2x plus 1. And this is going to be, if I factor this thing apart, it's going to be 2 parentheses. This is going to be x plus 1, x plus 1. And so that's an x-intercept. And what does that power 2 on that little parenthesis mean?
It bounces.
It bounces, right? It's that multiplicity test. Am I passing through it? Am I bouncing off of it? I'm bouncing off of the -1 for an x-intercept. In fact, that is the lowest point. Okay? Because it is actually turning around at that exact moment. So I can already tell you right now my minimum is at -1 comma 0. Does that make sense? Like knowing how a parabola works. Knowing like the graphing of it.
Why don't we just divide everything by 2?
Well, I mean, that's what I did. I factored it out. You can't just divide and make it disappear, because I don't have a number on the other side. You have to keep that equation the way it's found. Because if you just divide it, it could be a different form. It could be shifted up, down, right, and left. So you have to keep the numbers where they're at. Question? Or somebody else had a hand up? Okay. Now, obviously, I picked this problem as an easy one, because, number one, if we just follow the rules we've learned, I can figure out that concept really quick, where there was really nothing to it, right? It turned around on an x-axis, right? If we did the method that we learned the other day on Friday, where you did completing the square. Completing the square could tell you where that lowest and highest point is, because what you do first is you set y to the other side, right? So f of x, and then what I do is I subtract the 2 across. You want to get the x squared, the highest degree term by itself. So I'm going to subtract the 2 over. I'm going to factor out any numbers in front of x squared if I had any. Well, I do. I have a 2 out front, so I'm going to factor that out. And now what I do is I do half the middle squared. So half the middle, so this is my triangle middle over here, this side right here. Half the middle is 1, I squared it's 1. You take that, you add it to the other side, or sorry, you multiply it to this number first, because you'd have to distribute. So this is actually a 2 sitting there technically. But you take it times the number up front, and that's what you add to the other side. So I'm adding a positive 2 to the other side. And so what this turns out to be is the actual formula, and this formula would actually give you the vertex. Well, this happens to be the exact lowest point, because this would be y plus 0. You wouldn't need that plus 0, but it would be 0 over there. On this side, I could factor this thing apart. It'd be x plus 1, and so the vertex is literally -1 comma 0. That's how we find the vertex. And so on this point, the vertex was the lowest point of that graph. All right, questions about a parabola? And you agree that those are simple, right? It's an easy way to do it. We have this other strategy that we have that I introduced Friday. It's called differential quotients. We did it back in pre-calc days. It was in chapter 1, section 2 or 3 when we first learned it. And the idea is that its method of doing this is really clever. What it does is it goes, okay, let's say you had a really complicated looking formula. Like this is simple. This is easy to look at. That's why I picked it. But let's say you had a really complicated looking formula. And it was kind of going all over the place, up and downs. And the idea is that they could figure out where all those relative max and mins are by just looking at where slope is. Where slope would be found. Because at this moment, what's slope at this very moment? 0. It's like a perfect horizontal line. Like over here, slope was negative. Over here, slope was positive. But right here, slope is 0. So what they do is they use the differential quotient. And they said, okay, the differential quotient will spit out slope. And if you know what your slope is, you can figure out all the spots where it would give you 0 for all the slopes. So it could actually give you more than one spot. And so you could find different places on a graph where you'd actually have peaks and valleys. And it's kind of a clever situation, right? How that actually works. Now what we're gonna do is we're gonna actually like put one together to make sure that we can just make up one on the spot and figure out where the peaks and valleys are. Okay? So that's that's my third problem today. Let's do one more of these, but I'm not gonna do a parabola. Let's do like a cubic function. And then we'll try something a little more difficult. All right, so I've got 2 problems left. That's all I want to do, 2 problems. Okay, so the next one. Let's get rid of the graph. We don't need that anymore. Okay, so let's do a cubic function. Let's go with x cubed plus 2x squared plus 4x plus 8. Let's do that. This is going to be my graph for this particular problem. Brown, wake up. So, all right. Now, what we're going to do is we're going to try to factor this thing apart and figure out where the actual, x-intercepts are and where we'd actually draw. Now, this is a cubic function, so I know one of the tails goes down, one of the tails goes up. Okay, so we definitely have something going on here. If I factor this apart, my y-intercept will be 8. That's about right here. 11, 10, 9, 8, okay. And my x-intercepts, if I pull these apart, I'm going to pull an x squared here, that's x plus 2. Plot a 4 here, that's x plus 2. This ends up being x squared plus 4, x plus 2. So it looks like on my particular graph, I have -2, there's an x-intercept. And it's passing through, so it's probably doing something like this. That's probably what it's doing. Okay. Now, at some point, there's a critical point where it changed from positive slope to maybe negative, or in my case, it looks like it's going positive, positive. So would this graph necessarily have a peak or valley? No, it could. I mean, it could, in theory. I could have 2 turning points. I mean, I could do something like this. I could do something like that, but in my case, it doesn't. So how would we do this problem? Why would we attempt it? Well, by doing this critical idea, by doing the differential quotient, what we're about to do, it can tell you where this inflection point was. This critical point where it changed from like positive negative. It might be at 1, or it might be at, what, -2 there, but it could be somewhere else. I mean, maybe the turning point's like up higher. Maybe it actually did some weird turn up here. And I'm just like guessing where it's doing this. Because this is my guess, right? I'm guessing that that's the drawing. I don't even know if that's a fact. I mean, it could be, maybe the 2 was here, that -2 dot was there, and it did something like this. And 8 was up here. Maybe it had some turning point, so there's actually 2 hills and valleys. So my differential quotient will tell me that. Now, obviously, this is a really complicated type of problem. Just to find out that maybe I don't actually have a turning point here. That could be tough to look at. Maybe there's not a hill and valley. So this is the idea what I can look for. So, differential quotient. That's where we do this. Okay, this is the part that you should probably be writing down if you haven't already. This is the differential quotient. Now, what we're going to use it for is we're going to do the limit. We're going to approach when my h, which is that distance from my critical point, I'm assuming this is my critical point, when the distance from my critical point is about as close as I can get, like almost 0. Okay? So as h approaches 0, I want to be as close to that critical point as I can be. That way I can figure out where that turning point is. Where it either went from like positive to negative, that type of thing, for slope. Okay, does everyone have the formula written down? Yeah, this is tough. This is a tough one. We're going to do a different example here in a minute that might be a little bit better. I'm going to pull one out of the textbook so we have some different hills and valleys to it. All right, so the first thing you have to do, you have to take the original function, which is that crazy thing, and plug in x plus h into it. Take the original function, that's this part right here that I'm doing, plug in x plus h into all the x's that you see. Does that look like the original function with x plus h plugged in?
Sure.
Okay. Then what we have to do is we have to subtract the original function. The original function was x cubed plus 2x squared plus 4x plus 8. This. Let's get rid of crap and eat it. Okay. And then this is all going to be over h. As the limit, as h eventually approaches 0. Or I get closer and closer to those hills and valleys. What this formula is going to do is it will give me slope. This will give me a formula. It will not be a single number. It's not going to spit out like 2. It's not going to tell me exactly where the hill and valley is. It'll tell me a formula to find slope over this curve. Because if you looked at my curve there, slope did change. It was slowly changing in different spots. So this could potentially help me figure out if I can find slope. Okay? All right, so, and I'll explain how I know if there's an actual hill and valley when we get there. Okay, so foiling this out, this is where you could write up 3 parentheses. You could use Pascal's triangle. You can do lots of different things. I'm just going to foil this off to the side so you can see this. I would normally on a piece of paper use Pascal's triangle, but I don't want to go through that method right now. Foil, this is x squared plus 2xh plus h squared. That's foiling the first 2 out together, foiling the back 2. It's x cubed plus x squared h plus 2x squared h plus 2xh squared plus h squared x plus h cubed. All right, so there's that. That's this menacing thing is that. So limit as h approaches 0, x cubed plus x squared h plus 2x squared h which those could technically add together, so like 3. Plus 2x squared plus h squared x's, which that also makes 3. And h cubed. Okay. So again, that's this part that I just did here. The next part is 2x squared plus 4xh plus 2h squared. That is boiling this out, distributing the 2 over it in my head. 4x plus 4h plus 8. And now subtracting all the original stuff. Alright, all over h. Now, what was the rule that we talked about Friday? How do you know if we did it right? Yeah, anything that does not have an h should cancel if you did these things right. So let's check. X cubed, gone. 2x squares, gone. 4x's, gone. 8's, gone. Everything left has h's in it, which it does. Perfect. I'm going to combine some like terms here because I went too long. I should have combined like terms a long time ago. There's 3x squares, h's. There's 3x h squares. There is h cubed. There's a 4xh, a 2h squared, a 4h. This is all over h. Format as h approaches 0. Okay. Questions at all about how I got to this point? I know I'm going really fast, sorry. Okay, now what do we need to do next? Divide h. Divide h's. So if we divide all my h's, here's what we have. We have what? 3x squared. We have a 3xh. We have an h squared. We have a 4x. We have a 2h. And a 4. I'm missing anything? Is that everything? I can see everything. Looks like everything. Alright, and this is all the limit as h approaches 0. Now, here's the idea. I got to this point, right? You agree that I don't have a fraction.
Yes.
I can plug in 0 now for h.
Yes.
Because h is going towards 0, right? So, at the point I've canceled all the h's are going to turn out to be zeros. What's left? There's a couple of things.
3x squared.
3x squared.
4x.
4x.
Plus 4.
Plus 4. Okay. There's my function. Now what this represents, this is my slope formula. That's the slope of this curve. Now you think, what do you mean slope? It's a formula that will give you slope. Slope is literally changing as you went over that graph. It was going from positive to negative. This is representing slope at any certain moment. So if I plug in a certain x, it would give me slope at that exact moment. What they call the instantaneous slope. That slope right now at that exact moment. Right? Well, here's the idea. How do I know if I have a hill or valley? So, how you know is if slope will equal 0. If this slope equals 0 at any point, then you have a certain hill or valley of a max or min to this graph. If this slope will equal 0. Well, can I factor this thing apart? Is it possible that I can make a 4 in the middle using a 3 and a 4?
No.
So right now that's a strike against it. Okay. So since I can't factor this, I'm just going to do the quadratic formula. That's what the quadratic formula does. It factors this for you and it gives you your answers for x's. Negative b plus or minus square root b squared minus 4 times a times c.
All
Again,
over
this is
2.
a, this is b, that's c. Yeah, all divided by 2 times a. And here's how I know that this does not have a hill or valley. I know all that work because you saw me draw the graph earlier. What happens inside the radical?
Negative.
That's a negative number, right? Because you have like, this is 16 times 3, which is 48. And that's a 16 minus 48, that's a negative number. since this is negative, this literally means, this is called a determinant, by the way. That determinant's telling me I do not have a peak or valley. Now you're thinking, work, we did all that work for that. We already saw it from the graph. You knew it earlier from the graph that it was kind of curving and I didn't know if it actually had a peak or valley. So this confirms I don't have on this particular graph. Now, thinking, why do we do all? Because it is important that we do find those moments. This graph means, since it doesn't have a peak or valley, it means its actual graph is actually continually growing. It's telling me it's not changing directions. That's what it's literally telling me. That means when I went back to that graph, that thing was increasing the entire time over that entire graph. That's why it's important. So that's data that I can interpret from that graph. And you agree that's kind of tough to look at. It's tough, right? Because I mean, you did all this work. You're like, God. I mean, look at this. I had to do a cube to like FOIL that just to figure out it didn't work, right? Now, obviously, one of the things we're going to learn in this chapter is a shortcut. We are going to learn a shortcut. That I'm going to provide you with that. Okay, something that I've learned over the years of doing it that will help you alleviate doing the colossal amounts of work that some problems require. Okay, so we're going to eventually learn that. For right now, I'm not going to give you like crazy problems. I'm not going to give you a problem that goes to a power 4 or something, because at one point we need to factor it in the first place, or I have to do quadratics to actually solve it. So we have to be able to handle those types of things.
Power
Yeah, I'm not going to do that. All right, questions at all about the concepts of what we're working on?
Nada.
Okay, I'm going to stop there today, actually. I'm just going to do 2 today. So, because it takes a long time to get through those. So.
So